Yeah, she's eating now. Okay, it's 7 o'clock, so let's go ahead and get started. Just in time for my cat to be fed, so she can stop whining. So good evening, everybody. How's everybody doing tonight? All right, so hopefully everyone's doing well. So today, oh, new announcement. No, what is the new announcement? Oh yeah. I did read that email. Yeah, so let me actually let me address that right now. Actually, yeah. So there was an email that was sent from the office of the provost today. So they've basically instituted a special kind of grading scheme for this semester due to the situation with the coronavirus. So because a lot of students and faculty have had their lives really impacted by the virus, what they're going to allow you to do is to basically allow you to switch later on, if you want to take this class or any class that you're taking from pass to no pass. So normally, this is a decision you have to make early in the semester, but because of the situation, they're going to be allowing people to make the switch from either from a letter grade to a pass or no pass later in the semester. So that's kind of the gist that I got from the email. So I haven't read it in detail yet. But if that's something that you want to do, then you're of course welcome to talk to me about it. And I'm always happy to discuss something like that. So I don't know the details on how that would affect your graduate standing and because I know you guys have to maintain a GPA for grad school. But I'm happy to kind of work that through for you if that's something that you want to do. Okay. But I think the email said you can kind of wait to make that decision until later on in the semester, after all the grades are in. I see. Okay. But if that's something you want to talk about, I'm always happy to talk about something like that. Okay. Okay. So today we're going to be starting something new. So we're going to be starting our unit on instability and transition. So this is going to be our second to last unit of this semester. Basically, we're going to be doing this for 2 lectures. We're doing this Wednesday and next Wednesday because Monday is our midterm, so we're not going to have a lecture that day. And then after next week, basically, we're going to be discussing turbulence for the rest of the semester. So turbulence is kind of a big unit. So, we'll be doing it for about a week and a half, which is, not enough to, to cover everything, but I think it's enough to kind of give you guys at least some working knowledge of turbulence, which is kind of my goal. Okay. So before we get started today, are there any questions about the upcoming midterm or just what we covered last time or just anything in the class in general that I can answer before we begin? Mm-hmm. Yeah. Right. So the exam problems, will be very similar. It's it's not going to go outside of the things that we covered in the lecture and on the homework. So if you understand the homeworks really well, then you should be good to go for the exam. And definitely make use of the past lectures too, because there's a big variety of problems that I can ask you guys about these. The homework covers some slice of this, and and the examples that we do in the lecture cover another slice. So definitely, reference all of those things. It'll be within that realm. So it shouldn't be anything that, you haven't seen before. It'll be, of course, a slight twist because, I can't give you the exact same problems that you've seen before, but, it'll be within those realms of the homework problems and the example problems that we've done together in class. Mm-hmm. Okay. Any more questions before we start today? Okay, so let's go ahead and get started. So the topic for today, instability and transition. Okay. Okay. So, again, kind of the same thing with vorticity. The kind of the goal for this unit is to kind of build up towards turbulence. You know, so turbulence, up to this point, we've kind of just discussed it as, a state of really chaotic and unpredictable flow that happens when the Reynolds number exceeds a certain, threshold. But we haven't really talked much about how flow actually transitions to turbulence. So even though a lot of times we describe it as once the Reynolds number gets over a certain threshold, then the flow gets turbulent. It's not really an instantaneous process that happens like that. So I think when I was taking fluid mechanics the first time, I thought it was a situation like this, where if you have laminar flow, you have fluid that's kind of going along like this. Okay. So you have here, I've drawn two fluid particles and their path. So, the way I kind of imagined it is, say that these two particles, they have some kind of, the way I imagined they have some kind of tracker. So, one fluid particle might say to the other one, it said, hey man, check our Reynolds number. Okay. And then the other fluid particle would like look at his watch or something. It's like, oh, shoot, our Reynolds number is really high. Okay. So at that point, the fluid particles, they just instantaneously change their mood. So instead of being, boring straight line people, they would just kind of just go crazy after that. Okay. So that's kind of how I imagined turbulence was, before I, went to graduate school and really understood this better. Okay. So that's, obviously that's not how it happens. It's not an instantaneous process, and it's not, the fluid particles themselves don't really know what their Reynolds number is. That's kind of something that we as humans kind of, develop to better understand fluid flow. Okay. So, kind of to talk about it more in detail, the way transition actually happens is that, whenever you have flow that's, flowing in any kind of capacity, what can happen is that there are always going to be these kind of small random disturbances or perturbations. Okay. Let me draw the next slide. Okay. So this could be due to things like, flow going over a rough surface, right? So if you, imagine your typical kind of surface of like concrete, right? So even though, when they laid the concrete down, they tried their best to make it as smooth as possible. There's always going to be a bunch of tiny like ridges and bumps that are on it that are, that are naked, that are invisible kind of to the naked eye. But if you kind of look at it with the microscope, those are always going to be there. So as flow, flows over these kinds of surfaces, and due to a bunch of other small factors, just kind of small blips here and there, there's always going to be these kind of small random perturbations that happen with the flow. Okay. So the difference between laminar and turbulent flow is kind of how these random perturbations are treated. Okay. So if the flow is laminar, then what we say is that the fluid is in a state of stability. Okay. And so when we say that the flow is in a state of stability, what that means is that when all of these kind of small random perturbations occur, then they don't really do anything. What happens is that their effect kind of decays with time very rapidly. Okay. And you contrast that with the kind of the other flow state that we know, which is turbulence. Okay. So turbulence is often described as an unstable state. Okay. And then within the context of these random perturbations, what happens is that any kind of random perturbations that occur, instead of decaying down with time, what's going to happen is that these are going to amplify. Okay. So the key words here are kind of decay and amplify. Okay. Because whenever you have fluid flow, you're always going to have these kind of small random kind of disturbances or perturbations, and depending on certain conditions, these perturbations either decay or they can amplify, depending on if it's laminar or turbulent. Okay, any questions on this before I turn the page? Okay. So what does that look like kind of visually, right? So let's draw kind of two situations here. So first, let's look at a laminar case. Okay. So say we have a fluid particle that's coming along, and right here, it experiences a perturbation. Okay. So it could just be a small kind of distortion in density, or small distortion in the pressure, whatever. Something might have happened to cause the fluid particle kind of wiggle a little bit. Okay? So if the flow is laminar, what's going to happen is that perturbation is just going to be kind of nipped in the bud right there. So the perturbation is going to knock the particle a little bit, but then it's going to come kind of right back to its normal path. Okay? So in other words, that perturbation will decay. Okay. Okay, so let's contrast that with the turbulent case, where the fluid particle is coming along. And at the same location, we'll say that we introduce a perturbation. And so in the turbulent case, that perturbation is not going to decay. It's actually going to amplify. Okay, so that small perturbation will turn into a slightly bigger perturbation, which is going to turn into a slightly bigger one, right? So this is, of course, really exaggerated. So it's not going to be as as extreme as this, because it's going to be interacting with a bunch of other fluid particles. But this kind of gives you the idea of what happens when a small perturbation gets amplified. So it starts small, and then it kind of starts to gain momentum and grow bigger and bigger. Okay? So one analogy that I'd really like to kind of describe the situation is if you consider a a ball, and then we'll consider it in kind of two situations. So let's consider a case where you have a ball that's kind of sitting at the bottom of a bowl of some kind. Okay. So you can do this at home. So you can take a ping pong ball, or you can take like a fruit, like an orange, and put it in the bottom of a bowl, and then you can poke your ball a little bit. Okay. So in other words, we can introduce a disturbance in here. Okay. So if we poke this ball a little bit, what's going to happen is because of the rounded geometry, that ball is going to come right back into its its equilibrium state. Okay? So we call this a stable situation. Okay? So then we contrast that with an opposite case. So let's say we take our bowl, we kind of turn it upside down, and then we put our ball or our fruit on top of this upside down bowl, and we kind of position it such that it stays there if we don't touch it. Okay. But then say that you balance the ball here, but then you actually do push it, or you introduce a perturbation, right? And so what's going to happen because of that downward slope is that ball, that small perturbation or that small velocity that you give it, it's going to accelerate more and more as the ball eventually falls off the bowl. Okay. Or in other words, it doesn't come back to its equilibrium position, and in fact, that small velocity perturbation that you gave it will keep amplifying and getting bigger. Okay, so we call this an unstable situation. Okay. So this idea of stability and kind of connecting it to kind of how we understand about laminar turbulence is kind of the theme of this week. Okay, So what we're going to do is we're going to kind of examine mathematically, how we can determine if a flow state is stable or unstable, or at least we'll walk through kind of the method. The mathematics get a little bit intense, so I'll kind of we'll kind of look at the process kind of from 10,000 feet, and we'll kind of skip to the results. But we'll talk about kind of how we got there, and then we'll examine this for different cases, and we'll see how this relates to turbulence, which is kind of where we're going to be going. Okay. All right. Any questions on this? Okay. So in a nutshell, why is laminar flow considered stable, or why does laminar flow decay these perturbations, and why does turbulent flow amplify them? Okay. So let's go back to kind of what we understand about laminar and turbulent flow from before. Okay. So from the beginning of class, we know that laminar flow happens when the Reynolds number is relatively small. Right? And if you remember kind of what the Reynolds number represents, the ratio of inertial forces over viscous forces. Okay? So when the Reynolds number is relatively small, I mean, it doesn't have to be on the order of creeping flow, like it doesn't have to be much less than 1, but it has to be, usually on the order of hundreds. Is usually relatively small. That means viscous forces are relatively strong compared to inertial forces. Okay. So then if we kind of take into account what we understand about viscous forces, that kind of helps us understand why this just dissipates perturbation. Okay, because if we think back to when we did unsteady laminar flow, we know that the viscosity of a fluid is responsible for diffusing momentum or transporting momentum in the fluid. Okay? So if viscous forces are relatively strong, what can happen sometimes is that small perturbation that occurs, right? Right. We can think of a perturbation as kind of like a small distortion or a small packet of momentum. Okay. Okay. And so the thing about viscosity is that it's it doesn't have a direction. So, and what I mean by that is that when this small distortion of momentum occurs, what viscosity is going to do is that it's going to take that momentum and kind of diffuse it in every single direction. Okay. Or in other words, what we can say is that it's going to take this small distortion and kind of spread it out over a large region of space. Okay. Okay. And so by this act of spreading out that small distortion momentum over, a large region of space, what that tends to do is it kind of tends to smear it out, or it kind of smooths out those distortions. Okay. So an analogy that you can draw for this is, say you kind of have a small pile of sugar that's on your countertop, or glitter, you can say. Okay. So say you have a small pile of glitter, and then what you can do is you can take your hand and kind of spread that glitter all over your desk. Okay. Maybe not your desk, because that's a pain, but maybe someone that you strongly dislike. So say you go to someone that you strongly dislike, you put a pile of glitter on their desks and you spread it out. Okay? And so by the act of spreading it out, that pile of glitter, it becomes a lot smaller because it's spread out over a longer area. And you don't have kind of a big focal point of glitter anymore. It's all kind of spread out over a large area like that. Okay? So for laminar flows, which have a relatively high viscous forces, because you're spreading out that distortion, it doesn't really have a chance to kind of gain any momentum and kind of grow on its own, because it's spread over a larger area. Okay? So another, another term that I'll use a lot in our turbulence unit is dissipate. So viscosity tends to have this kind of dissipating effect, where kind of anything or any disturbances that occur, it dissipates that. So it kind of suppresses it and kind of pushes it down, so it doesn't become a problem. Okay? So then let's contrast this with turbulent flow, right? So turbulent flow, we know that the Reynolds number is relatively high. Okay. And we know that when the Reynolds number is relatively high, then inertial forces are going to dominate. Okay. So inertia is kind of the opposite thing of momentum. I mean, of viscosity, right? So while viscosity will take some disturbance and kind of spread it out over a large area, what inertia will do is it'll take that disturbance and kind of just push it to a different area. Okay. So say that we have a disturbance like that. Okay. So we know that turbulent flow happens when the velocity is really high. So when the velocity is really high, it's going to take that kind of disturbance and kind of just push it down the line. So it's, it's kind of the same thing as, taking, something that you have to deal with and kind of just pushing it down the pipeline. Okay. So while that may be okay for now, what tends to happen is that if you do that, then you have another disturbance, and you kind of push it into the same area, okay? And you have another disturbance, and you push it into the same area, okay? Oops. Okay. So you take basically a bunch of these small disturbances, and since you're not dissipating them, you're not really, getting rid of them, and you're kind of pushing them all into the same place because the velocity is all going in the same direction. All these little perturbations tend to add up, and they become a bigger perturbation, okay? So when inertia forces are really high, then all these small disturbances, they don't really get a chance to dissipate. All they do is just they get pushed down to some later portion where they all kind of add together and accumulate and become one really big disturbance. Okay. And so just from observing it, kind of when we're looking at turbulent flows, because of this, what it looks like is that turbulent flows are amplifying these disturbances. Okay. Any questions on this? Okay. Okay. So that's kind of the qualitative argument for how laminar and turbulent flows kind of deal with disturbances. So how are we going to analyze this mathematically? Okay. So what we're going to do is we're going to take our usual conservation equations for conservation of mass and conservation of momentum, and then into these we're going to introduce small disturbances. Okay. Okay. So, we have things like the continuity equation, we have Navier-Stokes. So if we introduce kind of small disturbances into these and they have a certain form, so particularly what we're going to assume is that these disturbances are sinusoidal in nature, just for mathematical convenience, okay? Okay. And then when we work through the mathematics of this, we should get something where it'll be obvious that, if as time increases, will the amplitude of these disturbances grow or will they decay? And that's exactly what we're going to do. Okay. Okay, so let's get into it. So the method that's often employed for this is called the method of normal modes. Okay. Where essentially what we're going to be doing is a Fourier analysis. So if you if you've taken if you've learned about Fourier before in a previous math class, that's kind of exactly what we're going to do. Okay. So in Fourier that Fourier kind of works in sinusoids, so that's kind of exactly what we are going to do. Okay. But before we we get into that, we kind of need to start with some definitions. Okay. So we know that we're going to introduce some small disturbances, and the way that we're going to do that is just we're going to simply add it. Okay. But we need something to add it to. Okay. So before we start the method of normal modes, we need to define what's called the base flow or the background flow. Okay. So the base flow or the background flow is going to be the velocity field that results if no disturbances were there. Okay. Okay. So basically, what this means is that the base flow is going to be our solution for the velocity profile, kind of as we know how to do. Okay? So if we look at kind of our lubrication case, okay? So just to jog your memory a little bit, so if we had a case where lubrication theory applied, then our velocity profile would look like this. So we have a minus h squared divided by 2 mu. Okay. Divided by dp dx times y over h, okay, times 1 minus y over h plus u h y over h plus u naught. Okay, so that was just the solution of our velocity profile if without any disturbances. Okay, so this right here is our base case or base flow. And then what we're going to be doing is, we're going to just be adding small disturbances to this. Okay? So often what's assumed is that the base case is steady. So the base case doesn't depend on time. Okay. So I just gave the example from lubrication theory here, but this you can apply this to kind of anything. So if we had Couette flow, or we have Poiseuille flow, or even something in cylindrical coordinates, the standard solutions to those kinds of problems would constitute our base flow. Okay. All right. Any questions on this? Okay. Okay. So in the method of normal modes, what we're going to be doing is we're going to take this base flow, and to it we're going to add a disturbance. Okay. So our disturbance has the following form. So I'm going to give the disturbances a hat. So our u hat's going to be our disturbance. Okay. So we'll keep it just totally generic. So we'll say it depends on x, y, z, and t. So that's all the possible variables. So we have our 3 spatial variables and time. Okay. All right. So it's going to be a function u of y times the exponential of ikx plus imz plus sigma t. Okay. And so we're basically just going to be adding this to our base flow. So what this means is that our total velocity, u tot, okay, is going to be equal to our u base, which is the function, say that if we're looking at a lubrication problem, that would be the function that I had on the previous page plus this disturbance function here. Okay, so we're literally just going to be adding these two guys together. Okay, so this formula for the disturbance has a lot of new parameters. So let's go ahead and define all of them. Okay. Right. So first we have our function that's out in front. So we have u of y. Okay. So the reason it's out in front is because this is going to be the amplitude of our disturbance. Okay. Because this is a complex exponential, we can use Euler's formula to basically turn this into sines and cosines. Okay. So if we basically have some function u of y multiplied by some complex form of sines and cosines. So because that u of y is out in front, this is the amplitude. Okay. So amplitude I think is relatively easy to understand, but it's I want you to kind of notice one subtle thing. Okay. And that's its dependence. Okay. So notice that this u is a function of y, and that's by design. And so the reason it's a function of y in this case is because this amplitude has to have the same variable dependence as our base flow. Okay. So from the previous page, we know that our base flow is only a function of y right here. Okay. So since our base flow is only a function of y, then our amplitude also has to only be a function of y. Okay. Right. So next we have k and m. So k and m, these are the wave numbers of our disturbance. Okay. So wave numbers is just kind of a fancy way to talk about the spatial frequency of the disturbance. Because we know that these disturbances are sinusoidal, so there's going to be some distance in between the relative peaks, and k and m are going to describe that. Okay. And then last, we come to probably the most important parameter that we care about, which is sigma, where sigma here is the temporal growth rate. Okay. So basically, the goal of stability analysis is to solve for this sigma. Okay. So in this case, we have an exponential. So there's no I in front of the sigma. Okay. So if this sigma was positive, then we would have a positive exponential. So we have an exponential of some positive number times t, so that we know as time increases, then the amplitude of this is going to increase. Right? But if sigma was negative, then we have a decaying exponential. So as time goes on, then the disturbance will decrease in amplitude. Okay? So the sign of this term right here will determine whether our whether our disturbances will grow or shrink. Okay. And I have kind of a table that kind of sums that up on the next page. But before I turn the page, are there any questions on this? Okay. Okay, so let's talk about that sigma a bit more. So sigma can be a complex number. Okay. Okay, so it can have a real part and an imaginary part. And then because of the form that we used previously, the one that we really care about is sigma real. Okay. So if you're doing a normal modes problem and you're using the form that that I put kind of previously, then you only need to solve for the real part of sigma. Right? So after this, I'll give you a different form of the disturbance called the wave number, called the waveform. Okay. Or wave speed form, I should say. But if you're using it in this form, you have kind of three different cases here. Okay? So sigma r is less than 0, then what's going to happen to our disturbance is that it's going to decay. Okay? And we know that if our disturbance decays, then we have a stable situation. So it's extremely rare, but you can get a situation where the sigma r is equal to 0. So if you introduce a disturbance, it's not going to decay and it's not going to grow, right? So it's just going to stay. So we call this situation neutral. Okay. And then the last case is if sigma r is greater than 0, then we know that the disturbances will grow, and then we know that if the disturbances grow, then this is a unstable situation. Okay. Okay. So that's kind of the first form or first way to perform the normal modes, is to use the previous form for u hat. So sometimes there's kind of a more convenient form for u hat. It's not that different, but it's kind of worth going over. Okay. And so this is the wave speed form. Okay. And it's actually the one that we'll use in the next, in the next problem. Okay. Okay. So once again, our u hat's going to be a function of x, y, z, and t. Okay. So out in front, we have our amplitude function, u of y. Okay. And this is going to be multiplied by an exponential, but then the form of the function in the exponential is going to be a little bit different. Okay. Okay. So inside the exponential, we have I, which is our imaginary number, times the magnitude of k. So let me kind of define this now. So k, with the bars around it, this is the magnitude of the wave number vector. Oh my God. Sorry. Can't go back. Hmm. Okay, that was weird. Okay. So before we define the wave number in terms of its components, where we just used k and m. So if you imagine k and m were two components of a vector, the magnitude of k is that the magnitude of that. Okay. So x here, this is the position vector. Okay. And then c is going to be the wave speed. Okay. So the kind of the kind of putting aside kind of the wave number and the position vector just for a second, kind of the biggest difference between the sigma form, which is what we used previously, you can call that kind of the growth rate form. The difference between that one and this one is that we have a minus sign right here in front of the time term, and we also have an I. Okay, so that kind of changes how we interpret the results of this. Okay, so let me turn the page now. Finally. So if we have this form, and we know that C is going to be a complex number, right? So we have C is equal to the real part of C plus the imaginary part, okay? So what we're interested in here actually is, because of the form of the disturbance, what we're going to be looking at is Ci, or the imaginary part, okay? Okay. So we have the imaginary part of C greater than 0. We know that we have an unstable solution. But if Ci is less than 0, then we have a stable solution, because the disturbances will decay with time. Okay. And then if you have Ci is equal to 0, then you have just a neutral situation. Okay. So the disturbance is just going to stay there. Okay. Okay. So what we're going to do is we're going to apply this method on one of probably the most famous fluid instabilities, called Kelvin-Helmholtz. Okay. Before we get into that, are there any questions on this? Right. So the question is, why do we use the imaginary part instead of the real part? Okay. So it's due to the form of the disturbance. Okay. So if we go back to this page right here, when we use the wave speed form, let me kind of clear things up a little bit. Okay. So you can see in the wave speed form, we have this imaginary number that's kind of sitting on the outside here. So when we multiply that through, we have inside here, we have an I times C. Okay. And so the reason we use the imaginary part is because the I multiplies by that other I, and it becomes, the positive one, like that. Yeah. They're really the same function. It's just they kind of just manipulate the terms just a little bit. Yeah. It's a good point to clarify. Mm-hmm. All right. Any other questions on this before we do Kelvin-Helmholtz? Okay. So the field of fluid instability is actually really interesting. So, of course, you can have instabilities in almost any flow, but if you if you talk to people who kind of work with fluid mechanics, there's a few what I call kind of famous instabilities that people talk about. Okay, so we only have time to go over one of them, which is Kelvin-Helmholtz, which is, I think, one of the cooler ones. But there's also things like the Rayleigh-Taylor instability, the Taylor-Bernard instability. So the weird thing about these instabilities is that they're not described by what their actual physics or what they actually look like. They're described by the people who discovered them, which I think is very vain and not helpful at all, because it's for you guys who are learning about Kelvin-Helmholtz for the first time, just by looking at the name, you have no idea what it's going to look like. But that's just kind of how they settled this. So the people that discovered it put their name on it, and that's kind of how we have to do. Okay, so Kelvin-Helmholtz, it's an instability that occurs at the interface between two parallel streams of fluid. Okay. Okay. So the geometry looks something like this. So we have an interface that kind of denotes two different zones. Okay. So on the top here we have a uniform flow. Okay. So we'll call this top section section 1. So we'll say that has a velocity u1 and it has a density rho 1. Okay. So that's density, not pressure. Okay. And then on the bottom of this interface we have a different fluid. So on the bottom here, say we have a velocity u2 and then a density rho 2. Okay. So the way I've drawn it here, the faster fluid is on top, but it doesn't always have to be the case. You could have a faster fluid on the bottom, or the faster one on top. But just to show that there's a difference between them, that's kind of how I drew it. And so what's going to happen, because you have differences in velocity on the top and the bottom, and oftentimes you're going to have differences in density on the top and the bottom too. What's going to happen is that the interface between these two are going to be unstable. Okay, so instead of being kind of a nice straight line like how I drew it, what's going to happen is that interface is going to start to break down and it's going to start to grow. Okay. Okay. So in other words, we're going to say that we have a disturbance at the interface, or a small kind of perturbation of momentum or mass or whatever, and then that disturbance is going to grow due to the situation that we're in. Okay. Any questions on this? Okay, so since we're in kind of a very special situation here, we have basically a flat uniform flow on the top and the bottom. So we're kind of, just for a second, kind of ignoring any boundary layer phenomenon. So one thing to note here is that the situation is totally inviscid, so there's no viscosity. Okay. And so because we have no viscosity here, because of Kelvin's circulation theorem, we know that there's no circulation or no vorticity that can be generated. Okay. So in fact, what we can say about the flows on the top and the bottom is that they're both irrotational. Okay. And what's special about irrotational flows, kind of like what you saw on the last homework assignment with the Thwaites method, is that we can define it in terms of a special function. Okay. Because of this, we're going to have both vertical and horizontal velocity components. And since we know that when we have to solve for multiple unknowns, it can be kind of a pain in the butt. One way that we can do this is we can put them in terms of a single scalar function. And that scalar function in this case is going to be the velocity potential. Okay. So the velocity potential has the symbol phi. Okay. And it's going to have the a dependence on x, y, and t. Okay. And so to get the velocity components, if you kind of remember from the last homework, is that we just take derivatives of this function. Okay. So to get the x velocity, we just take the derivative with respect to x, and then for the y velocity, we just take the derivative with respect to y. Okay. Okay. So now that we're using this velocity potential, let's define the base flow, or the base or the background flow for the top and the bottom. Okay. Okay. So for uniform flow that just goes in one direction like this, the velocity potential is pretty simple. Okay. Okay. So we can say that phi1 base is just going to be u1 times x. Okay. Okay. And then phi2 base is going to be the same thing, except it's going to use u2. Okay, so let me just make this a little bit neater. Okay. So then, you know, if we start to introduce a disturbance to this, all we have to do is we're going to add a disturbance to the velocity potential to these base cases. Okay. So what we can say is that the total velocity potential in zone 1, this is going to be u1x, which is our base case, plus phi1 hat, where phi1 hat here is going to be our disturbance. Okay. Okay. And then our total phi2 is going to be the sum of, you know, this our base case and a disturbance for 2. Okay. And so what we can do is we can plug this into our governing equations and then solve for the relevant parameters. Okay. All right. Any questions on this before I turn the page? Okay. Okay, so for phi1 hat and phi2 hat, we're going to use the waveform form of this. Okay, so let me write out the formulas for that. Okay, so phi1 hat is going to look like this. So since our base flow depends on, we'll say it depends on y, even though it's just a constant. Okay, we're going to have a1y times exponential times ik times x minus ct. Okay. So that's phi1. So now let's define phi2. It's going to have the exact same form. Okay. So phi2 hat is going to be a2 of y exponential of ik times x minus ct. Okay. Right. So from these disturbances, you know, since we know everything about the base flow already, what we're aiming to do is basically to solve for the unknowns in this, you know, in our disturbances. So we have 4 unknowns here. Okay. So our unknowns are going to be a1 of y. Our second unknown is going to be a2. Okay. We have an unknown for k. So k is remember the wave number of the disturbance, which is this kind of the spatial frequency. And then most importantly, c. So c is going to be the wave speed of our disturbance. Okay. So you'll notice that, you know, we share the same wave number and we share the same wave speed between phi1 and phi2. You know, and kind of the reason for this is because we're finding the disturbance at the interface. So the interface is basically going to be shared in between the 2 fluids. So any disturbance there will have the same wave number and it will have the same, you know, wave speed. So the reason they have, but the reason they have different amplitudes is because we have 2 different fluids. You know, the amplitude is going to be different, you know, either above or below the interface. But at least, you know, the wave number property and the speed property are going to be the same between both. Okay. Okay. And so because we have these 4 unknowns, we're going to need 4 equations to solve for it. Okay. So luckily, we can apply 4 boundary conditions here. Okay. All right, so our first 2 conditions are going to be the far away conditions. Okay. So similar to how we did our unsteady, you know, flow of a plate, you know, as we get really far away from the plate, then we basically assume that things are at rest. So kind of the same thing here, where as we get really far away from the interface, then the disturbances will basically go to 0. Okay. Okay. So our third condition is kind of known as the kinematic condition. Okay. So what that says is that the velocity of the interface has to be the same. Okay. So because the interface is shared by both fluids, then if we compute the velocity of the interface in one fluid, it has to match the same one in the other one. So that's basically what this condition states. Okay. And then the last boundary condition that will apply is basically dynamic matching. So the pressure pressure at the interface is going to have to be the same in both fluids. Okay. So we basically can't have any step changes in in pressure. So as we go across the interface from one fluid to the other, we don't experience suddenly a big change in pressure because we should have dynamic matching there. Okay. Okay. Any questions on this and the boundary conditions that we apply? Okay. Okay. So we're not going to run through the math of putting those boundary conditions into place. So we're just going to skip to the result. So remember, when we're doing stability analysis, what we're looking for is the term that's in front of the t. So in this case, since we're using the wave number form, we're interested in the wave speed. Right? So if you apply those conditions and you work through all the kind of the really tedious algebra, you end up with the following result. So you get the wave speed c is equal to rho 2 u2 plus rho 1 u1 all over rho 2 plus rho 1, okay, plus or minus g, where g is gravity, g over k, times rho 2 minus rho 1 all over rho 2 plus rho 1, okay, minus rho 2, rho 1, u2 minus u1 all over rho 2 plus rho 1, this quantity squared, and then everything in the square brackets raised to the 1/2 power. Okay. Right. So it's a bit of a long expression for C. Okay. But depending on the size of C and the relative signs of it, then this is going to determine our behavior. Okay. Right. Okay. So one thing that kind of the first thing that I want to draw you guys' attention to is that within this expression here, notice that I never put any i's. There's no imaginary number here. So under certain conditions, this C is going to be purely real. Okay. So if this C is purely real, then we have Ci is equal to 0. So we have basically a neutral situation. So when we have a neutral situation, then any disturbance that happens at the interface will basically just stay. It's not going to grow or shrink. Okay. But interesting things start to happen when you look at things in the square bracket. Okay. Because you notice how things in the square bracket are square rooted. Okay. And one of the most popular ways to get I is if you have square root of a negative number. So we start to see some instabilities if the quantity underneath the radical or in the square brackets becomes negative. Okay. Okay. So in other words, if we have G over K times rho 2 minus rho 1 all divided by rho 2 plus rho 1, okay? If this is less than rho 2, rho 1 times U2 minus U1 all over rho 2 plus rho 1 squared, okay? So if that condition is met, then we can start to have some instabilities. Okay. All right, any questions on this before I turn the page? Okay. So we can rearrange the terms around in this a little bit just to make them a little bit easier to work with. Okay. Because right now we kind of have densities on both sides of the sign, and we have things are we have fractions. So usually this is put into a form that's a little bit more convenient. So kind of the Kelvin-Helmholtz criteria is given by this. Okay. So if the quantity on the left, which is G times rho 2 squared minus rho 1 squared, is less than K times rho 1, rho 2, U2 minus U1 squared, then we basically have an instability. Okay. Okay. Right. So let's kind of put some words onto this just to make things a little bit easier to interpret. Okay. So basically, we're going to have an instability if okay. So I'll describe kind of three different cases here. So the first case is if the velocity difference is big enough. Okay. So notice on the right-hand side there, we have U2 minus U1. So if that difference between U2 and U1 is really great, then the right side of this inequality is going to be, really big. So in that case, then the quantity on the right is going to be bigger than the quantity on the left. Okay. The second case, which is actually one of the more interesting ones, is if the difference in densities is small enough. So remember, this is talking about the difference in density. So kind of the the most extreme case here is if rho 2 is equal to rho 1. So if actually you have the same fluid on the top as on the bottom, then you're always going to have an unstable case, which is really interesting. Which is kind of what you would not expect. So if you have the same thing on the top and the bottom, that actually would lead to more instability than if you had a different fluid on the top and the bottom. Right? So then the third case is with regards to K. Okay. So K, remember, is the wave number. So if the wave number is high enough, then we have an instability. Okay. So a high K basically corresponds to a high spatial frequency. Okay. So what that means is that if your disturbances are kind of small, closely packed like this, then that has basically a high K. But if you have a case where your disturbances are far away, then that's kind of a lower case. So the more closely packed your disturbances are, then you're more likely to have instability. Okay. Okay. So up there is the kind of the general case, but there's kind of some interesting limiting cases. Okay. So let's first look at a case where both the top and the bottom have the same or at rest. Okay. Or in other words, U1 is equal to U2, which is equal to 0, okay? Right, so in that case, we have our wave number is going to be equal to plus or minus G over K, rho 2 minus rho 1, all over rho 2 plus rho 1, okay, square root. Okay. So we're going to, so, you know, in the case where we have U2 is equal to U1, then that second term is basically going to go away. And so remember, you know, the same kind of rules apply, where if this C turns out to be an imaginary number, then this will lead to an instability. So this will lead to an instability, or the only way that this is going to become a negative number is if we look at the differences in density. Okay. So remember, rho 2 corresponds to the fluid on the bottom, and then rho 1 corresponds to the fluid on the top. So if the fluid on the bottom is more dense than the fluid on the top, then that's going to lead to a stable solution, because then our wave speed is going to be a real number. But if we have the more dense fluid on top, then what's going to happen is that the more dense fluid is going to, you know, by the action of gravity, going to want to come down, and then that's going to create an unstable interface. Okay. So I'm going to draw that on the next page, but before I do that, are there any questions on this? Okay. Okay, so just kind of just to summarize what I just said. If more dense fluid is on the bottom, then this is stable. If the denser fluid on top then unstable. Okay. So let me just kind of illustrate what you know, what happens when you have the denser fluid on top. Okay. So if you have the denser fluid on top, then by the action of gravity, what's going to happen is that it's going to want to go down. Okay. And so by conservation of mass, as the denser fluid goes down, then the lighter fluid is going to come up. Okay. And so because you have this constant, you know, transport of fluid across the interface, and it doesn't really do this in kind of an orderly way, then what's going to happen is that the interface is going to become unstable. Okay. 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 And so the other interesting limiting case, we kind of hinted at it earlier, as if the top and the bottom were the same fluid. Okay. So if the top and the bottom are the same fluid, then their densities are going to be the same. Okay. You know, assuming that we have kind of negligible differences in temperature. Okay. So if the top and the bottom are the same, then we have rho 1 is equal to rho 2. Okay. So then if we apply that assumption to our wave speed, it will look like this. Okay. Okay. So we have C is equal to U1 plus U2 divided by 2, plus or minus U2 minus U1 divided by 2 times I. Okay. So because we have this presence of I right here, then this is always going to be unstable. So if you have a situation where you have two of the same fluid that are kind of going over each other like this, and as long as there's some difference in velocity between them, then that's going to cause the interface to become unstable. Okay. Okay. So let me, you know, now that we've gone through the mathematics, you know, I want to kind of show you what it looks like in practice, because I think, you know, that's kind of the coolest part of Kelvin-Helmholtz. So let me draw it first, and then I have a kind of a video to kind of illustrate kind of what I'm showing. But before I do that, are there any questions on this? Okay. Okay. So now let's get to the visual part, which is kind of the coolest thing about Kelvin-Helmholtz. So what tends to happen with Kelvin-Helmholtz is that interface in between the two fluids, it becomes what's called a vortex sheet. Okay. And so what that means is that there's vortices or vortexes are going to form on that sheet, and it's going to produce this kind of really cool looking wave pattern. Okay. So let me just kind of draw the kind of the progression of this. So at first, when the instability starts, it's not going to look that exciting. It's just going to look like a sinusoid. Okay. So it might look like that. Okay. And the reason for that is because you have vorticity that's basically being generated here. So each of those peaks, you can kind of think they're trying to rotate in the clockwise fashion. Okay? And so as those peaks tend to rotate more through the action of the instability, they start to form these wave patterns. Okay? Okay. So, you know, that what starts as kind of a small sinusoid, as those as the instability grows, or as those disturbances, you know, amplify, then it starts to form these, and eventually they'll start to curl in on each other. Okay? So they start to look like this. Which is probably going to be the most artistic thing I ever draw in this class. Okay? So you can actually observe these in nature if kind of the conditions are right. So actually, I have a video to kind of show. So let me share my screen. Okay. So can everyone can see my screen? Yes. Okay. All right. So here's kind of a kind of small news, you know, cast to kind of show in action. Right. So you can see from the video, you know, because exactly kind of what we said, where you have this difference in velocity between the top and the bottom, that leads to, you know, the Kelvin-Helmholtz. So even though there was a difference in density, that was basically overcome by the differences in velocity. Okay. Okay. So that's all I got for you guys today. Oh, no sound. Oh, sorry about that. But you guys were able to kind of see the clouds that were, you know, that were kind of doing in that form, right? I'll post the video for you guys, so you guys can see it. Okay, so we're out of time. Next time I will see you guys is a week from today, because Monday we have our midterm. So remember, Monday I'm not going to open up a Zoom meeting. I'm just going to post the midterm. And just like we talked about, you'll have 24 hours to do the midterm. Okay? So I'll see you guys next Wednesday. So best of luck on the exam. So if you have questions, I'll be available through email. I'll be available through email for all the way up until the exam. But have a great weekend, everybody. And I will see you on next week. Stay safe and stay healthy out there. Right, so the question is, what time am I going to post the midterm? So I'm going to post the midterm at 7 p.m., so right when class starts, and then you'll have until 7 p.m. the following day to finish it. Thanks, Louis. Have a good weekend. Okay, I'm going to sign off.